I'm going to kick this off. Welcome, everybody. Good morning. I'm very delighted to be here to present our ECE Rising Stars Alumni Award lecture with awardee Dr. Scott Hanson. A quick word on this award. This was established about 5 years ago, recognizing younger ECE alums who have achieved early successes in academia, government, industry, private organizations. Awardees are seen as engineers to watch within the greater science and engineering community and being nominated up to the age of 35. With that, let me say a few words about Scott. Scott is the CTO and founder of Ambiq. He invented Spot. This is Ambiq's core subthreshold technology platform to enable the world's most energy-efficient chips during his PhD studies at the University of Michigan. He founded Ambiq in 2010 and led the development of the world record-setting Apollo. This is Ambiq's first flagship processor. Under his leadership, Ambiq has shipped more than 100 million chips to the world's top brands and has grown into the global leader in ultra-low power solutions. In addition to his role as CTO, he has played various other roles leading product definition and development, managing product production test, and most importantly, spending a great deal of time with customers to understand their needs and their vision. As a widely recognized innovator in low-power circuits, Scott today leads the development of Ambiq's technology roadmap. His pioneering work in subthreshold design and picowatt processors has been widely published, with more than 30 leading publications, more than 20 patents on related technology, and a wide variety of speaking engagement. His work was honored by the University of Michigan with the 2014 Arbor Networks PhD Research Impact Award, and he is our most recent EC Alumni Rising Stars Award, and he was also honored by Ernst & Young as an Entrepreneur of the Year 2020 finalist. With that, Scott.
Thank you. Please. Yeah, and I'm sorry that was such a long self-provided bio there in the intro, but it's good to be here. I did my undergrad here, master's and PhD. I started in 2001, and I was, Dennis, I was doing the math, and I realized first of all, it's been 20 years since I started, and I realized that you, my thesis advisor, were actually younger than I am today both when I started in your program and ended. So that's like a real mind blower for me to know that I'm now older than all that. So as a midlife kind of guy, I'm now here to give you a little bit of insight on my journey building Ambiq. So Ambiq was a company that I spun out with Dennis Sylvester and David Blaauw from university. We've grown that company significantly. I want to give you some insight into my journey, talk a little bit about the technology, talk a little bit about what I need from you all, from the people who are dialed in here to continue to grow that company. And I'll leave plenty of time for questions at the end, hopefully. So first of all, who is Ambiq? Ambiq is a company that we founded to put chips everywhere, and it's actually in the name, AmbientIQ, ambient intelligence. And what we actually sell is chips. We sell chips. We bundle that with software. It is timing chips. It's microcontroller chips. It's wireless chips that have microcontroller plus radio inside. And increasingly, it's heavily multi-core SoCs that can do all sorts of things. So it's the thing we do best is energy efficiency. We build lower power chips than anybody else out there. And we do that using subthreshold circuits, and we'll talk more about that later. I'll show you the kind of simple marketing view. I'll go maybe a little bit deeper on the technology side. My guess is that many of you know what this is, but we've used that core technology to grow very quickly. We, as I said in the title there, we're at over 100 million units at this point shipped. The numbers in excess of 130 million units at this point, and we're shipping many millions of units per month. So the rate is really fantastic, something I never could have imagined as a student here. And so I want to give you a bit of insight, as I said, on that growth. But the exciting opportunity now is we always wanted to make things intelligent, but neural networks, since I founded the company, have really come a long way to the point where not only can we connect things and sense things, but we can actually take that data and make useful decisions with it. So there's a lot of exciting opportunity ahead. And the vision, the big vision, is intelligence everywhere, as I said. And there's all sorts of angles on this. It's not any one thing. It's not wearables. It's not just hearables, but it's a million different applications that we could consider. I'm showing a couple really big opportunities. The on-risk doctor. So today we're in millions and millions of wearables. I'll name a couple specific customers later that are publicly disclosed, but let's just say that most of the wearables that are being shipped right now probably have an Ambiq chip inside it. And the first generation of wearables was very much about step counting and very simple stuff. These days, they're starting to get a bit more intelligent, but where we need to be is it needs to be a doctor. It needs to be telling you that you've got a problem coming. It needs to be diagnosing anything you have. So contact tracing in the COVID era would have been trivial had we just kind of turned all of these things on everybody. In fact, it's been shown that these watches can actually detect COVID as it's coming on before you even know you have it yourself. So that opens up some pretty fantastic opportunities, and the more intelligent we can make these things, the better. We could do the same thing in the industrial world. So take that same set of electronics, throw it on a piece of industrial equipment, monitor it for changes, look for the vibration signature to suddenly change and detect an anomaly, and then flag a repair person to come out and correct that. And there's a million other things that we could look at spread throughout the smart home, in hearables, in headphones, in smart commercial use cases. Point is, we want to put intelligence everywhere. And at the core of that is power, right? If you want to put things everywhere, you need a battery. Batteries are small, they're expensive to replace. And so we want to run with as little energy as possible. And so the core innovation that we brought to market was subthreshold circuits. And I apologize for this. I'll get to real technical stuff later. This is a marketing slide that we share for people that don't know much about circuits, right? In typical digital computing, we represent zeros and ones with voltages. So we might have 0 for 0 volts. We represent a 1 with, say, 1.2 volts, 1 volt, whatever. The problem is that energy is voltage squared. So we get a lot of energy spent by having to go all the way up to that 1. If we can instead swing our voltage much smaller, we get quadratic savings. So if we instead go to, say, 0.3 volts, in this example, we can get 16x savings. That's pretty exciting and pretty useful. Turns out, as I'll discuss later, it's really hard to do. It comes with all kinds of challenges that have scared away a lot of other companies. We've taken that on, though, and that gives us a bit of a superpower. We can go out and build things with lower power than anybody else can. Okay, so today I want to do 3 things. One is I want to give you a bit of insight, my journey in building the company. Hopefully there's at least one wannabe entrepreneur out there who wants to go do this and can take some value from what we've done. I want to tell you a little bit about our technology. I know that many of you come from the same lab that I came from, and so maybe you don't care about, you know about all this stuff, right? But there will be others that might care. And I also want to give you a bit of a peek at the future, what we're working on and where we could use your help. I wish someone had told me 10 years ago that my company was going to still exist 10 years from then. So we're trying to take a view that we will be here 10 years from now, and so planting the seeds in academia to figure out that next gen of technology is important. Okay, so first of all, it all started here at University of Michigan. That's exciting. Here's a posed photo. This is not actually what our lab looked like on any given day, as you guys will appreciate, but you see the 2 professors, Dennis Sylvester and David Blaauw, talking casually in the background, a lot of us working diligently in the foreground. But this was this group of people that invented the core technology, and what we were building was devices like the one shown on the right, and that lab has gotten considerably more sophisticated in what they've been able to build, but the idea was we wanted to build cubic millimeter computers that could be implanted, say, in an eye for intraocular pressure monitoring. And it was, as you can imagine, low power that can fit in cubic millimeter has a battery that is sub-cubic millimeter. That's really hard to do. So we were able to do some incredible low power work here. That required subthreshold operation. It required all sorts of other innovations. And a lot of the early work that we did, though, before we could go build little 3D systems, was exploratory. So I said earlier that dropping voltage improves energy efficiency. Well, a lot of the early work was saying, how low can voltage go? So if you look at the plot on the left there, for those interested, is a SRAM butterfly curve. The fact that we see two eyes in the curve, we see overlap, suggests that it can store data. So this one was taken at 65 millivolts. This was work done jointly with IBM. And so the cool thing there is at 65 millivolts, transistors work, bit cells work. This fundamental building block of a chip, the bit cell, it works. So that's pretty cool. There's a whole other question of should we operate there if we can. But we went and built processors. We built custom 8-bit processors, it was pretty cool. We went out and built these things, and they operated down to 160 millivolts in this particular case. And there were all sorts of different variants of this. But we got a lot of mileage early on of just exploring the limits of low voltage. We eventually figured out you don't want to go operate at the minimum voltage. There's some other voltages that are potentially more interesting. But the biggest thing you're facing is process variation, temperature variation. We're exponentially sensitive to variations in temperature and process, et cetera, and voltage. The plot on the left shows an IV curve for a transistor. In the blue case, say in nominal conditions, the dashed line shows what happens when you shift the VT of the device by 100 millivolts. And that's a pretty big shift, although in today's latest technology nodes, maybe not. But in that case, you get a 14x change in performance in the subthreshold zone and an almost nominal change in performance in the so-called superthreshold zone. So we're dealing with, process changes can cause us to have 14x variation. That's really hard to deal with. How do you build millions of chips, right? It's actually comparatively easy to build one chip that works at room temperature and you get your ISSCC publication in your PhD, right? That doesn't work in the real world, right? So there's a lot of these problems that we solved at the university, a lot that we subsequently solved at Ambiq, but this is what we're fighting, and this is really what the core technology is about. It's about solving all these problems, and we have marketed this as something we call SPOT. Academics will kind of, you'll raise your eyebrows at that and say this is silly, but it's a way to describe the whole collection of techniques that we use to make all that subthreshold operation possible, to fight the process variation, to do production test, how do we do timing closure, how do we build memories. So it's a lot of pieces. It starts at the transistor level. It includes analog circuits, digital circuits, memory, production test methodologies. And the thing I like to tell people is that we've built this kind of collection of pieces. It's 50 things or 100 things that we do differently than everybody else. There's no one silver bullet that makes it all work. You got to do it all right in order to be manufacturable. And that's something that we did partially at Michigan, partially here. And that's collectively what we refer to as SPOT. And so we founded the company in 2010. Again, promotional picture of the three founders on the left. Big paper or cardboard check with me on the right. And for those who don't know, that's Tim Draper, who is really one of the most famous venture capitalists out there. And very successful venture capitalist. So that was really cool that we got them to invest what is, in hindsight, a very small amount of money of $250,000. We've raised something like $200 million as a company, which is astronomical and scary. And for those of you seeking to build a chip company, that's often what it takes to be an independent chip company. But there's value in that, right? Okay, so I want to take you through a couple phases of Ambiq. We were nominally a hardware company. We said we're going to go build chips. The piece of that little 3D cubic millimeter computer that was ready is the chip piece of it, the microprocessor. And so we went out and we built our first product. It was an RTC, a real-time clock. This is like the simplest, least sexy thing that you could possibly build. But it was a way for us to showcase our core technology. So we launched that in 2012. It was used by millions of smart credit cards and all sorts of other markets. You probably are saying, hey, Scott, I don't have a smart credit card that has electronics inside of it. Well, you probably have a passive smart credit card, but there are, in fact, millions of smart credit cards floating around out there that have little displays, and the 3-digit CVC code in the back is rolling. So every 15 minutes or 45 minutes it changes. We're the technology inside all of that. And so we've shipped a lot of that. It was, I'll show you how many transistors and what process node, et cetera, are inside this thing, but it's a really small chip. It was one we could build with like 5 or 6 people. And we did it. So it was a way for us to say, there's this SPOT technology, everybody's suspicious of it, but here's a product that shows that it's working. From there, we took a step up. So it took us about 3 years to really get this to market, but we built a microcontroller. So we added in an ARM core Many of you are probably using ARM cores today. We added in a bunch of memory. It was a huge leap in complexity. Okay, we weren't, in hindsight, we were not prepared for this. It was stuff that we hadn't anticipated coming out of Michigan work. It was stuff we hadn't anticipated in doing the real-time clock design. Fantastically more complex. We had to come up with all sorts of interesting solutions, but we made it through. And this is actually shipping in millions of fitness trackers, utility meters, watches, et cetera. You can go to Best Buy today and probably still buy products with that chip inside. And then I'm going to just fast forward to today. We have another enormous quantum leap in complexity with our most recent product. This is our so-called Apollo 4 product. This is a multi-core processor, so it has an MCU, it has a GPU, it has multiple megabytes of memory, it has MRAM, so non-volatile memory in the form of MRAM, has a Bluetooth radio. It runs at close to 200 megahertz at peak speed. This is so far above what we used to be building here, and so far above even what we built at Ambiq that astounds me. But this is the nature of this business, right? So one of the lessons that I've seen or that I've learned is this business is a treadmill. Once you get on that treadmill, you can't get off. You have to keep innovating and keep delivering the next thing. Everybody talks about Moore's Law. Moore's Law has been that engine that kind of keeps that treadmill moving for everybody. And if you don't stay on that treadmill, your competitors surely will. And the good news is we have core technology that allows us to stay out ahead of those competitors. We've done so, but you have to play that same game. And that's especially true in consumer electronics. We're very heavily present in consumer electronics. I'm wearing one of my customers' watches on my wrist today. And those design wins are constantly shifting, constantly changing what they need. So Moore's Law moves very, very fast. And I want to just really put some numbers to it. So our three products, this is over a 9-year period. Okay, we went from the RTC product in 2012 to the Apollo MCU in 2015 to Apollo 4 in 2020. And we had a number of generations of Apollo in between. Okay, but we started at 0.18 micron. We jumped to 90 nanometers. We did a couple products at 40 and are still, in fact, doing products at 40 nanometers. And now we've got a product that's actually a SIP. We've gone to 22 plus 40. So it's a SIP of a 22 nanometer die with a 40 nanometer die. At the same time, the transistor count has gone up by 3 orders of magnitude. Okay, so we've gone from roughly 100,000 transistors to roughly 10 million transistors to well in excess of 100 million transistors. I don't actually know the official transistor count, but it's enormous. And the memory density has skyrocketed. What's also astounding to me is in a period of 5 years, so from 2015 to 2020, we increased our processor speed by 8x, and we increased our energy efficiency by 9x. So we got both faster and a whole lot more energy efficient. So you take the same 10 megahertz thing and run it on those two processors, and it's going to be 9x more efficient in Apollo 4 than on the original Apollo. And you've got plenty of headroom to go. So this is amazing. This is in part an observation about Moore's Law. So I guess my one takeaway is if there's a way to do whatever problem you're solving digitally, be very afraid of that, right? If yours is the analog approach to a digital problem, Moore's Law can certainly catch up. So that's something that we take to heart, and we seek to exploit that now, right? So at 22 nanometers, I like to say that MIPS are free. So MIPS meaning millions of instructions per second. I can give my customers free processing power, free in the sense of power consumption. So you can add as many MIPS as you want to your product, and it won't compromise the battery life, it won't compromise the experience. Turns out that's really powerful. And that's what I want to talk about next. Specifically, we started as a hardware company, and we realized pretty quickly that we actually needed to be a solutions company. So you'll hear this. This is actually kind of a boring statement at this point, but most chip companies will tell you, we thought we were a hardware company, but it turns out we're more a software company than a hardware company. Ambiq today employs, I have the number later, but it's over 160 people, and of the engineering team, we are definitely, the software people outnumber the hardware people at this point. Chip design people are outnumbered by software development people at Ambiq. And so the part two of this is we built a bunch of chips, we scaled them on Moore's Law, but we realized pretty quickly we had all this free MIPS that we had to put to work, okay? And so we had to build software, we had to build a solution. And so the question is, what do you do with all this free MIPS? What do you do with the solution? Well, Endpoint AI is how we're categorizing it. And the vision is exciting. Some of it's the stuff I already talked about, but I want to collapse Amazon Echo down to a sticker. It should be, instead of a big wall-plugged column that is in your kitchen, it should be a little sticker that's in every room in the house. We should have the Star Trek computer that we can talk to, and it should be battery powered. All sorts of preventative maintenance opportunities, on-risk doctors, on-risk personal fitness coach. That's a big one that's of interest. Real-time translation, facial recognition everywhere. That one maybe creeps me out a little bit, but there are good and important applications for that. In short, there are huge opportunities for the companies that can take free MIPS and can attach a useful solution to it, do inference in a reasonable power budget, at a reasonable cost budget. There's enormous opportunity for companies that can do that. And one of the opportunities that we've been pursuing specifically is voice recognition. And that's, a couple years ago, is one of the areas we sat down and we said, we've got free MIPS, how are we going to put them to work? Well, voice recognition is coming, let's get into it. And there's a couple markets that are really demanding that. So gaming controllers was one. Certainly wearables, smartwatches, bands, et cetera, is another. People want to talk to Alexa on their wrist, right? Remote controls are to some extent going away. You've got TVs that you can talk to today. You've got Alexa close by, but increasingly you can also talk to your remote controls. Headphones, everybody's walking around with headphones today. Walking around campus, I'm sure half of you walked over here with earbuds in. And so that's another area where we want voice control. And then there's just all kinds of smart sensors in the smart home, the smart building. It's voice control, so Alexa, what's the weather today? But it's also context awareness. So knowing that Scott is giving a talk right now, and so we should probably deactivate his incoming messages, right? It's knowing that the person is outside running on the road versus inside working out in the gym. And it turns out that doing all of this in the type of chip that we build is really, really hard. It's what I like to say is it's a microwatt, megahertz, kilobyte, and cents problem. So this is actually a teardown from one of our customers' products, publicly available. Our chip is one of the chips there. And when you break this open, you can see it's pretty modest hardware that you've got inside. This is not a phone. It's certainly not a PC. And so you can't do the things that you can do in a wall plug Amazon Echo. You've got a power budget that's a couple hundred microwatts to maybe a few low-digit milliwatts. You've got processor speeds that are maybe tens to hundreds of megahertz, maybe a couple megabytes of memory. And this is an important one. You've got to probably fit all of this chip BOM into $5. So chip bill of materials probably has to fit in sub $5. So if we're going to put voice everywhere in wearables, remotes, et cetera, and to scale to even billions of devices, we have to match or beat the price economics of a smartwatch. And in fact, there's probably not room for another chip in that bill of materials. So you've got to find a way to add all that voice recognition hardware inside one or more of these chips that already exist. And we also like to say that it's a signal chain problem. So doing voice recognition, it's very easy to get enamored with inference and say it's all about AI. Everybody loves to build the best inference engine out there. But there's a whole signal chain that leads up to that, right? You have sensors. So we found actually, for example, when we went and built our signal chain, we hyper-optimized it. Less than 10% of the system energy usage was actually inference, the determination of whether somebody said Alexa. Most of it was buried in the microphones, in the ADCs that talk to those microphones, in the signal pre-processing that has to happen. In subsequent to inference, there's decision making. So, okay, now that I detected, I think somebody said, Alexa, what's the weather? I need to decide what to do with that. Do I package that up, send it to the cloud? Do I, what other decision could I possibly make? There are security protocols that need to be followed. There's just general OS work that needs to be done. There's then communications. You have to get the data off chip. It's not enough to just kind of listen and hear. Usually there's a cloud back end of these things, so you've got to have a radio there. You've got to probably have a display. And then this is one that people often forget. There's a battery there that's sitting at maybe 4 volts, maybe 3 volts in some cases. You've got to convert that down to voltages that are usable, and you've got to do so efficiently. So there's a complete signal chain here. And the takeaway from that is you can't be an inference company. You can't be just a hardware company. You have to be a solutions company. And that means covering from sensor to security to inference, hardware on up to software. And even that software bleeds into the cloud, right? So it's not just embedded firmware that's running on the microprocessor. So we at Ambiq have had to take all of that on. And in fact, we built something we call Voice on Spot. So this is a solution for voice everywhere. It's a combination of our Apollo microcontroller series coupled with a bunch of software that does Bluetooth, handles all the Bluetooth stack. It does connectivity to the cloud. It does keyword recognition and beamforming and all sorts of other interesting audio stuff. Every single component has been hyper optimized for energy. I won't get into performance numbers today, but we did some internal software and algorithm development. So Ambiq now employs people whose job it is to build algorithms, which is amazing to me. We're not just a hardware company. We're not just a software company. We're an algorithm company as well. And some of it is licensing from the outside. So one thing I learned pretty quickly is if you're going to be a solutions company, you can't do it all. You can't be simultaneously the best-in-class low-power chip designer, best-in-class software designer, best-in-class cloud software designer. So we've, in some cases, taken on hard problems ourselves. In some cases, we've outsourced that to third parties who are close partners. And so I guess the conclusion of all this is Ambiq is not just a hardware company. In the last 4 or 5 years or so, we have evolved into more of a solutions company. And that's an evolution that continues as we speak. Okay, so I want to put it all together and flash forward to today a little bit. We were a hardware company. Now we're a solutions company, and we're very much an international company. So we have in excess of 165 people now at the company. We're spread across U.S., Asia, Europe. In fact, a lot of our business is in China today. A lot of our business is in the U.S., a lot of business in Europe. So we're very much a multinational company, and that's something that's impossible to do. You can't be a chip company and be a U.S.-focused or Europe-focused or whatever. You have to be a multinational company. And I'll just say it's been a challenging few years, right? U.S.-China relations are at a tense point right now. It's very important that we have a continuous supply chain that covers the U.S., Taiwan, and China. And we're doing our best to navigate that. We're navigating it very well. We've got close partners in all those geographies. So, but with us becoming a solutions company, we've had to become a multinational company. And we've brought our technology to a lot of really great products. So a lot of the logos here are blurred out, but we've got a couple that are uncovered. Huawei is a big customer of ours. I can say that there have been publicly available teardowns that show Fitbit to be a customer of ours. Garmin, similarly, there are teardowns that reveal Garmin to be a customer of ours. We've done a lot of announcements with Oppo. So for those of you, a lot of the US-based people are not going to know Huawei and Oppo necessarily, but these are two of the biggest companies in the world and ship a lot of cell phones and a lot of wearables. We've worked with animal tracking companies. So this is a new niche market for us that's actually not so niche. The volumes that are coming out of our customers in this space are really exciting. They're tracking cows. They're tracking pets. They're tracking all sorts of interesting things. So we're also getting into car accessories. We're getting into all kinds of analog watches, smart home devices, utility meters. But the point is we've brought intelligence to over 100 million battery-powered things at this point. And increasingly, the customers are looking to us not just to be a chip provider, but a complete solution provider. So we're selling them hardware, we're selling them chips, but that comes with a whole bundle of software, and that software is vital to making us successful. Okay, so we've gone through this evolution. We've shipped a bunch of volume. We're having really nice commercial success, but where do we go from here? Well, we definitely want to go make Endpoint AI happen. We're not making it happen yet in the way that we've envisioned, right? Where the products that our customers building our customers are building are wonderful, they're exciting, but they don't quite yet realize the full potential of all these things that we talked about earlier. So I want to give you a really good example. So we are very interested in the headphone space. This is one of several spaces that say very similar to wearables. And the headphone of the future, maybe looks the same as the headphone of today, but it acts very differently. So, first of all, it's always sensing. So we're always listening for voice. We're always listening for sound, ambient sounds. We're letting in some ambient sounds, not letting in through others. You're listening to high fidelity music you're hearing conversations that are happening around you, and we're constantly running inference locally. So we're reacting to local voice commands, and it should be if not actual NLP, maybe it's emulated NLP, where maybe I can't understand any conceivable word, but I can understand maybe 1,000 commonly used phrases that correspond to tens or hundreds of actual commands that you're trying to achieve. It should these devices should perfectly cancel out ambient noise, but then they should have the capability of letting in certain sounds. So think about neural network-driven source separation that can identify that there are 5 different speakers in the room, separates out those 5 voices, realizes that there's 5 other sounds of interest, maybe a car idling nearby, a dog barking nearby, a baby crying nearby, and can optionally enhance those, let those through. So if I'm out for a run, I want to be able to hear the car noise coming through. If I'm in a bar having a conversation with my friend, I want to hear my friend's voice, but I don't want to hear everybody else talking in the room. This all should be achievable on the fly. I've included translation on the fly. This is not a hyper latency sensitive problem. It's one that's, I think, important to mention. It's probably happening more on the phone than it is in the earbud, but it's certainly part of that vision. And then at the same time, though, this is also a communications device. So it's streaming audio maybe from my phone up to my ear. It's streaming my audio down to the phone so I can have a discussion. All of this has to be done with the minimum power. We want these things to be always on devices that you wear all day. You should be wearing them in our talk right now so you can really hear me. I shouldn't have to wear a microphone, right? You should be able to hear me talking quietly, and it enhances up. This is the kind of thing we want to enable, and there's vision versions of this. So I want to add a camera to certain devices, all kinds of biosensors that we want to be adding. There's a lot of problems that get very complex. They involve sensing, they involve inference, they involve communications, and so where I need help from you, from the researchers in this audience, is in a couple different areas. I want zero energy sensing interfaces. So I say zero. We laugh at the company, because no power number any vendor or my engineers could ever give me would be acceptable. They could say, XYZ circuit consumes 100 microwatts, and I would say, okay, I need it to be 100 nanowatts. And they would say, well, I got 100 nanowatts, and I'd say, okay, it's got to be 100 picowatts. So we joke that 0 is the only acceptable energy number. And so I want sensors that are sensing audio, so microphones. I want, and the associated ADCs. I want imaging. I want cameras and the associated analog to digital conversion. I want all sorts of health sensors. So I've seen some really exciting things lately around biological sensing. So ECG, EEG, glucose sensing is certainly interesting. I don't know if it's feasible non-invasively, but I would love to see that. I want zero energy inference stack, and I say stack because it's not just the hardware. I want hardware accelerators that run at minimum energy. I want them to plug into standard frameworks too. So I don't want your accelerator if it comes with its own custom framework. Custom compilers certainly okay, and I want this accelerator to be able to support standard neural network architectures. I want it to support the standard frameworks, the standard training frameworks like TensorFlow, PyTorch, but I want to see innovative network architectures too. So as a hardware person, I tend to focus a lot on hardware and making hardware as best as it can be. But I've realized pretty quickly that one bad line of code can completely torch an otherwise beautiful design. And so building good networks, architecting them correctly is critical. So innovative network architectures, but also the way those architectures are implemented in software is critical. And then I also want to see compilers and network optimizers that are effective. We've seen a lot of interesting companies start to pop up and offer this, but I haven't seen a solution yet that works. And then on the training side, most of my customers are afraid of neural networks. They want them in their products, but they don't want to necessarily train them themselves. They want to buy good, known, working neural networks from somebody else. That's going to change really quickly as they get more experience and as young engineers graduate having learned all these things at school, learn to use TensorFlow at school, et cetera. So I would like to see a complete stack up of expertise that kind of culminates in optimized networks, in training data that can accompany that, in simple flows that allow embedded engineers to quickly prototype up neural networks. and then ultimately to implement them on hardware effectively. So this is a big one. I've spent a little bit more time talking about this one because it's very important, and I'm not totally happy with the options that we've seen off the shelf thus far. And then finally, communications is always important. Today, we're primarily working with short-range streaming. So we have Bluetooth is generally the radio that people are using for us, Bluetooth or Bluetooth Low Energy. And that's going to continue to be there. So I generally I'm not that interested in your wild, crazy custom radio scheme unless it can be coupled with Bluetooth or Wi-Fi or one of the other standards. So think a lot about standards-compliant radios. And I'm interested in Bluetooth and Wi-Fi in particular. So those are the two that in the smart home, in wearables, in hearables, and all sorts of other things are going to be the dominant radio standards. There's also an emerging area of low power, wide area radios. So think cellular grade radios that can communicate over kilometers, miles, and it would be technologies like NB-IoT. So this is part of the new cellular standard is this narrowband IoT standard. It's very, very low power. It's capable of transmitting at great distances, so we get really high transmit powers. LoRa is another good example. So that's one that's actually technically proprietary, although widely used and becoming more of a standard. But low power wide area is also interesting. So I've got not everything I'm going to sell is going to be for a watch or a headphone or something else, say in a smart home. Sometimes you have to go out to the distant oil pipeline and be able to broadcast over long distances. So low power wide area technologies are of great interest. Wake up radios are also interesting. So I said before, I don't want your radio unless it will couple with a standards compliant radio. Wake up radios can do so, right? So I'm interested in cool wake up radio technologies that play well with Bluetooth, with Wi-Fi, et cetera, and will do so when the other end is not using your proprietary solution. So you have to be able to use whatever radio technology you've developed. I want to make sure that it can talk to today's iPhone or today's standard base station. Okay, so that's one way you can help me. Solve cool research problems that I care about and tell me about it. The other way I want your help is come work at Ambiq. We're 165 people. We're hiring a lot of people. We're probably going to hire, I shouldn't even put a number to it, but we're going to hire many people in the next 6 months, the next 12 months. And there's a good Michigan bias at Ambiq today, but we really haven't done a good job of recruiting new college grads out of the bachelor's program, master's program, or PhD program. So I encourage you to come work with us. It's fun. The thing I can say about a startup is, and I have to be careful. I don't call us a startup anymore. We're a private company. Okay, we're past that stage where you don't know if the company is going to survive and live to tomorrow. Right? We have revenue. We have real customers. We have a stable workforce. But as a small private company, the thing I can tell you is you come in and you're going to get a breadth of exposure that you will never get at a big company. Going to work at the big companies, and I won't name them, but the big companies that are all here recruiting you, it's wonderful. This is a great place for you to land. They offer wonderful salaries and all this, but you're going to get relatively narrow exposure. You're not necessarily going to get an idea of what the system architecture looks like. At this company, everybody's sitting around the same table. We're all participating in driving the architecture. People can walk into my office post-COVID, let's say. They can walk into my office anytime they want. Pre-COVID, they can walk into my office anytime with a cool idea, and we can talk about it, right? Maybe it results in a patent. Maybe it results in some new feature of our chip. So that's what you get out of a small company like this. I'm going to leave it there. If there's questions, I'd be happy to answer them, but I appreciate everybody's attention.
Very much for a fantastic presentation. Questions?
So we do have one virtual question. I will just note there was some difficulty with the microphone, so if you could just repeat the question before you answer.
Oh, no.
That would be helpful. No, yours was fine. It was just the introduction.
Oh, okay.
So you're close enough, so if you could just repeat
Perfect.
the question for me, that would be great. So the question is, do you have to get special device models from fab to generate the libs, or the normal models are good enough for the sub-threshold characterization?
Oh, that's a really good question. And I had a slide in there that addressed this and then deleted it in the interest of time. But the answer is yeah, what we call S2S, the spice to silicon correlation, is horrible, or traditionally has been horrible. We collected early on a lot of data to show that, and we actually established a really tight partnership with TSMC early on, and have continued to work very closely with them. So you saw all the fabs. The only fab I mentioned up there was TSMC. So we've exclusively been using TSMC, and we do a couple things. One is we've worked with them to help them understand where the models are wrong and where they need to be fixed. We told them what operating points we really cared about so they could go fit these models. I mean, look, fitting, now that they've pulled back the covers on how SPICE models are fit, it's not that complex, right? It's just, they're just kind of, they're choosing the points they care about, and they're fitting their model to the points that they care about. So all we had to do was give them a few more points to care about and a few more points to weight in their analysis, and the result has been that the models are vastly improved. They're still nowhere near where I think they need to be, but we have means of correcting for that in our timing flow. So that's a big piece of especially our digital timing flow, is accounting for the S2S problems that we've seen. And it's always a problem, right? We care about levels of current that our competition doesn't, and so sometimes we're micro-optimizing things that most of the foundry users don't care about. But that's why there's a barrier between us and the rest of the world. It's why other companies are not necessarily catching up with us. So I think the situation has improved considerably since we started the company, but it's still not perfect. And frankly, I like it that way. I want it to be hard so that I've got some advantage over my competition.
We have one more virtual question.
Mm-hmm.
How do you select a technology node, and how much does the price of that play a role?
Yeah, and that's a big one. Price, you hit on it. That's the question was about how do we select a technology node? How does price factor in? Technology node is very much an economics play. So, I mean, frankly, if I wanted the most energy efficient transistor, I would use the most scaled FinFET I could find. I would use a 3 nanometer device or 5 nanometer device, very small. I'd run it at super low voltages, and actually the leakage gets to be better. FinFET is it's a wonderful transistor, but it's a really expensive transistor. It requires double patterning, so the mask count is through the roof. So I'm going to say that economics is a big piece of it, and specifically economics, for us at least, for deeply embedded computing, it's around, I need to find the thing that gives me the lowest cost or near the lowest cost for a mix of RF, embedded non-volatile memory, a lot of logic, a lot of analog. So you have a real mix. Increasingly, I'm going to say that memory does dominate our die area. So increasingly, we're seeing SRAM and MRAM dominate our die area. But that piece of how much is this thing going to cost in the end has been a big driver. And that may not be true in, say, industrial spaces where there's a bit more elasticity around pricing. But in consumer electronics, we do tend to get, well, let me put it this way. It's very hard to charge a premium in consumer electronics. You get a design win based on really exciting technology, and then the customer will generally tell you, but you need to, I'm paying you the same price I paid my previous vendor. And there's wiggle room there. Sometimes you can negotiate them up, sometimes you can't. But you have to be at a point where your cost is at parity with the competition, or at least close enough to be at parity with the competition. And so that drives node selection in a big way. But there is some level of flexibility, right? There's a product, for example, I could decide to make a product at 40 nanometers or 22 nanometers. The 40 nanometer version might be slightly cheaper because maybe it's a RF heavy product that uses big transistors. But if it's within a few percentage points in cost, then maybe it's a win for us to go to 22 because I say, hey, I'm an energy focused company. I care about energy. 22 nanometer transistor is smaller. So let's just say it's a complex equation. It's increasingly pushing us to multi-chip modules. So like I showed earlier, we've got a big compute and digital die that is 22, and then we've got an RF die that's at 40. That will, in future products, I think you'll see a mix of both monolithically integrated radios and analog at 22, as well as multi-chip solutions like that. So it's becoming really interesting, and as much as I've said we've become more than just a chip company, we're also becoming, to some extent, a packaging company, right? You have to packaging these things together in an economical way is challenging. So, good questions.
When you're pushing really hard on these Is that something you can do with the relatively standard fabs, or do you have to work with the fab companies to do
Yeah, it's a good question. So the question is, we're pushing the transistors to new places. Do we have to work with special fabs? Do we have to modify the process in any way? First of all, we can work with any fab. It is certainly, there's some overhead to building a relationship with a particular fab. We don't have to modify the process at all, so that's the good news. Or at least, let me say that we've taken great care to make sure that we don't need to modify the process at all. And so that allows us to use the same low-cost process that everyone else uses. It allows us to get, at some point, especially today, capacity is a massive problem. I don't know if you guys have heard, but there's a chip shortage going on, right? But there's a massive capacity shortage, and if we were in our own specialized node, we would have just been absolutely in the worst situation possible. Good news is we're in standard process. As for fab selection, we went with TSMC at the start because they're the best out there. We're taking enough risk as a small, early stage company. Don't take a risk on fab, right? So we went with TSMC. But knowing what we know now, I think we can go with alternative fabs. We certainly have at times explored that and looked at the implications. It wouldn't be, necessarily the easiest thing, but we have a methodology for how we port from node to node. We've gone from 180 to 90 to 40, now to 22, and we're looking beyond 22 right now. So we have a methodology for porting nodes, and I could just as easily apply that methodology to porting foundries.
There's one question. How and why did you decide to focus on wearables versus other IoT applications?
Okay, good. Okay, the question from Dave Wensloff is, how and why do we decide to focus on wearables versus other IoT applications? It's a good question because he founded a company around the same time and went and focused on broader IoT applications. So I'd love to hear his answer to the question. My own answer is, in the case of wearables, that was a market that had big volume potential and was willing to take risks and really cared deeply about power. So you've got a tiny battery on the wrist. They were running out of steam with their current microprocessors. They were really excited about the potential of getting a lower power microprocessor, and they were willing to take a risk. A big conservative company that's in an industrial space has to necessarily be a little bit more careful about what new technologies they adopt. If a new wristband has some development hurdles or runs into a problem, you answer first, Scott. Dave Wensloff says. If you run into problems, it's not that. Let's just say that the stakes are a lot lower for a wearable. I want to be careful how I say this because we take every customer very seriously and we treat it like a life or death situation in solving their problems. But let's just say they're a little more risk tolerant. Wearables customers have been. Their volumes are very quick and have been very quick to emerge. So, we're shipping, as I said, many millions of units per month right now, and that's largely because we took a chance on a consumer market that cared about innovation and cared about battery life and maybe was a little more risk tolerant. The broader IoT is something that we're very interested in now, and I think we're actually in a position, now that we've reliably delivered silicon to wearables for a while, we're in a position where we can take on some of the more conservative IoT customers. And we already have a lot of those, right? So we're shipping into utility meters, we're shipping into all kinds of smart home applications. We have some lightweight automotive applications that we're being used for today. So there's medical companies using us. So at this point, the real challenge to expanding beyond wearables and really getting a solid revenue stream in these other markets, it's more of like a documentation thing. In order to reach all these other markets, you have to have software, you have to have reference designs for here's how you design your utility meter. You need to support a Zigbee stack and not just a Bluetooth stack. So there's a whole bunch of collateral that comes with branching into these new markets, and that's something that we're getting ready to go do or have been doing for a while now. Thanks, Dave.
Where do you think there is room for innovation in low-power hardware? I hear that software is more decisive now in Ambiq than hardware. What are your thoughts?
Well, I think there's a ton of opportunity for innovation in hardware. I mean,
Could you?
oh, okay, sorry. The question is, where is there opportunity for, or is there opportunity in an innovation for hardware? We heard a lot about software becoming important. Is there still opportunity in hardware? Absolutely, 100%. I mean, at this point, hardware and software, in my mind, the same thing, right? I mean, I want software innovations, I want hardware innovations, and I think that there's low-hanging fruit on both sides. So I hope I didn't give the impression that we're becoming a software company. We're a solutions company, which means we have to give equal focus to the hardware and the software. But specifically, I see sensors as still consuming far too much power. Microphones in particular are just horrendous on the power side. There's some interesting technologies coming, some of which we're developing internally. Imaging is another one. I mean, just to get a picture on chip is hugely energy consuming, right? To take video, get it on chip, and then analyze it is really, really power hungry. Some of that can come in the form of better algorithms and better software, but I would love to see better camera chips. I'd love to see better interfaces, better ISPs to process all that. So imaging, audio, I want to get those on chip better. And then still communications takes a ton of power. Sending stuff off chip. A lot of my job is try to figure out how do we send less data over the radio so that we don't have to power up this big power hungry thing. And so we're trying to do local compute. We're trying to do inference locally so that I don't have to send raw audio up to the cloud. So give me a way to stream audio over a conventional Bluetooth link at 100 microwatts and I'm going to be really excited, right? It's really hard, especially when I bound you into using standards compliant protocols. It's really hard. So I'd love to see that. I'd love to see a lot of the technologies we're seeing deployed in radios. It's more the same. It's people who have been designing radios for tons of years, and they're just really good at squeezing out milliwatts and microwatts from the radios. But they're still using basically the same basic, architecture that we've seen for a long time. I've seen some interesting things in the MEMS side. So super regen radios have been combined with MEMS elements. That's really interesting to me. But I'd love to see whatever other perpendicular approaches you have to radio design that are out there. So sensing and communications, those are two ripe areas for innovation.
Other questions from the audience?
Yeah.
So, in the early days of starting the company, would you qualify, or I'm interested in the challenges that you face. So technical challenges versus non-technical challenges, right?
Yeah.
So technical challenges, getting yields, to be reasonable given the variability issues and moving from one chip that works to every chip that needs to work. Or non-technical challenges like raising money from investors.
Yeah.
Is that the hardest thing?
I mean, it was all...
Getting the people that have been in the industry for 20 years, building tons of chips to come listen to you as head of the company when you're like a 28-year-old kid coming out of school.
Yeah. So the question is what was hard early on in the early days? Was it technical problems like getting yields up, building millions of chips? Was it pitching to investors, telling our story, et cetera? And of course, the answer is all of it. Probably the most challenging thing is that being a founder CEO is it's really lonely. You don't know if you're doing a good job. I didn't as CEO, my employees, while we're friends maybe, but they're not really, they're not my colleagues, right? They're my employees, they report to me. My board members, investors are similarly can be friendly, but they're not necessarily completely aligned with me. So I was alone. And I'd never seen a CEO work before. I don't know what the heck a CEO is supposed to do, right? So that's the really hard thing. And so every day I woke up, to be very forthright about this, I developed an anxiety problem. And I can tell you guys all privately about that another time. But it's very hard, right? You don't know if you're doing a good job. You get selective reinforcement from the people above you and below you. But you're constantly questioning yourself. And a lot of it is because I know how to design a chip, but I don't know how to manufacture it at scale. I don't know how to pitch to investors. At the time, nobody really wanted to invest in chips. So the world has really changed. I mean, right now, raising money for a hardware startup, and if it's AI oriented, if it's inference oriented, or data center plus AI oriented, it's a lot easier to raise money than it was when I started. Back in my day when I started, it was really hard. But it was challenging to do all that stuff, and I'd say the best skill you can, there's two skills you can have as an entrepreneur that I think are really valuable in those early days. One is you have to be good at learning new things. Actually, PhD program is really good at that. PhD program teaches you how to learn, and you're treated relatively independently. You're left to be, at least in, let's say the way, Dennis, you ran your group was, I had a lot of freedom to do the things I wanted to do. That was good training for being an entrepreneur. The other thing, the second thing I think you need as an entrepreneur is you need to be almost naively or stupidly persistent. You just have to keep going and keep breaking through walls. I've looked at a lot of companies that have made it or not made it. Now, luck plays an enormous portion, so I don't want to be up here and say everything I've done is because I'm an amazing entrepreneur. No, it's because part of it is because we've been persistent. We've just kept going. We've come up against a lot of walls. COVID was a crazy thing that we faced. I mean, who could have predicted it? Nobody could have predicted that, okay? U.S.-China relations degrading the way they have, maybe some people could have predicted that, but it's been a huge problem for us that I can't go and influence U.S. government policy. The best I can do is I'm like a little mouse while elephants are fighting. I navigate between their feet and try not to get stomped on. So all you can do is you can keep running up against the wall and hope you break through, and you can be that mouse running between the elephants. So being adaptive and a quick learner is good. Being persistent and stupidly persistent is also good, right? You have to just not worry about what if XYZ happens, right? You might fail, and the good news is most of the people here, you'll have a degree from the University of Michigan, one of the best universities out there. You'll be very highly employable. In today's market, you can go get a job anywhere you want. But if you have the means or the opportunity to go start a company or participate in a startup, do it. It's fun. It's been a lot of fun.
Great answer. I'm very tempted to leave it at that, but I will ask the last question, which is, Scott, what would it take for you to relocate Ambiq to Michigan?
What would it take to relocate Ambiq to Michigan? Yeah, that's a good question. I had ambitions. I'm from Michigan. I grew up in Southeast Michigan. I did all my university work here. I don't think we're not going to relocate, but setting up an office here is actually something we should probably consider. I think there's a lot of good people here. It's probably time to do that. We could be closer to the research, a lot of the research work that's happening. So I'll give you credit. If we do, you'll get all the credit. Okay.
And I will take that.
Yeah.
Well, thank you very much, Scott. This has been fantastic, and thank you all for coming.